Awesome. Cool. So scraping UCLA at scale, how Hotseat helps you craft the perfect schedule. So this is us. I'm Nathan. That's Tim. As Eugene mentioned, we're both UCLA alums. We both graduated last year, June 2021. Tim's in grad school now, kind of work in industry, but we really got interested by the problem of course enrollment while we were at UCLA. I think we've probably done like, what, 24 quarters of enrollment between the two of us. And I know we've both had trouble getting into classes that we wanted to enroll in. So we thought there has to be a better way to kind of enroll in classes. So this is Hotseat. This is a screenshot of one of the courses. And our goal of Hotseat is to kind of like give you all of the information that you need to know to make the best enrollment decisions for you. So we have reviews of professors, we have information about the class, we have data about enrollment. Here's like a little list: every class offered every quarter, grade distributions, enrollment charts, professor reviews, notifications. We tell you course tips, and we have dark mode even. So yeah, we've been working on this for a while. We've packed a lot of features into it, and we are really proud of the result, and we hope you find it useful. So a brief history of Hotseat. So I started this project about 2 years ago. There was a class I wanted to get into that I didn't. And so I thought I'll scrape some data from the registrar to like figure out how quickly classes fill up. And that turned into an independent study project I did for my digital humanities minor. And I kind of like left it at that. I, shared it with some friends, showed it on like Reddit. Everyone thought it was super cool. And I was kind of there, ready to retire it then. And then Tim came along and he was like, hey, this idea is super cool. We should make it like a website. And so I said, okay, I'll do it if you work on it with me. And we've been working on it for, I guess, just over the past year. We kind of made Hotseat. We launched it last spring, just right as we graduated, which is ironic, I know. And we recently launched a super big update with text alerts. So we text you when classes open up. Like I said, our mission is to give UCLA students the information to make the best enrollment decisions for them. So we're all about the information, giving you all the like ingredients you need to craft your perfect schedule. We're gonna do a quick live demo briefly. So like I mentioned, the URL is hotseat.io. You can check it out. You can search like any class you want. So like let's search like CompSci 136 is a class I really liked at UCLA. So it tells you intro to computer security. We just updated it, so we have this winter's classes, so it's like super useful. We have reviews for you. We tell you like, oh, there's a group project involved. There's one midterm, the finals during finals week, so you can kind of start thinking about those things right away. And I think like our main like flagship feature is this enrollment progress. So you can see like, oh, like if I want this class, I'm going to need to first pass it, which I think is super useful. We have reviews. We tell you about the textbooks. You can star a class, and then you can go put it in like your My Courses section. You can subscribe for notifications on the class. So I can get text messages about that. I'll do that. Awesome. And yeah, that's basically Hotseat. So it's like kind of meant for you just to explore the classes that you're interested in, find all the info that you need to know. Let's go back to the slides. So yeah, text notifications, and the link takes you directly to my UCLA, so you can roll directly. And we have a special ACM promo code. So the way you get notifications is you have notification tokens. You can get them by writing reviews. But if you sign up this week, we give you 4 free notification tokens because we like you and we assume you probably came from this talk. So go sign up. That's the website. Okay, so enough of the plug. How does Hotseat work? So you may have heard this a couple times now. We've mentioned web scraping or scraping. What exactly is scraping? So if you go to a website, like the UCLA registrar website, you'll see a page like this, right? And it has all the info that you need to know about like classes or whatever you might be interested in. If you're a computer, what you see is this. This is like the HTML that actually backs that page. We can kind of see there's like header that says like intro to computer science. There's like some JavaScript in the middle of there. There are some more headers. This is what the browser reads and renders so that you get that. Web scraping is basically taking this format and transforming it into this format. So this is a screenshot of the Hotseat database for that intro to computer science class. So you can see we've kind of like parsed out like the relevant details from here, like the title, the number, the description, the subject area, and then we have some extra data about like when it's created at and stuff. So that's the like main idea of web scraping is we're taking like pages on the web, we're kind of reading them like a computer reads them, and we're taking the bits of info that we want from those pages and saving those into a format that we can use and parse and use in other ways. So with Hotseat, obviously there are a lot of courses and classes at UCLA. So we kind of have to do this at what Tim and I have dubbed scraping at scale. So basically we periodically scrape data from the UCLA registrar website every hour, and we do that via a set of AWS Lambda functions. And we'll kind of talk about those in a bit if you aren't familiar with that. And those scraper functions get the data and they parse it just like how we talked about. And they store it in this database. We use PostgreSQL specifically. And then we make that database available to our main web application, which powers the website, which runs on Ruby on Rails. And you can kind of see we have like some stuff on AWS. We run the Ruby on Rails website on Heroku. We have like another database for search. And then down there at the bottom, your computer interacts with a Ruby on Rails website, and it kind of handles all these other processes in the background. So this is, I've been calling it our buzzword slide, where we just have all the technologies we use. So Ruby on Rails, Tailwind CSS, React TypeScript, and D3 on the front end. We use AWS, specifically AWS Lambda, which is a way of executing like small bytes of code on AWS. And we specifically use a language called Go that powers those AWS Lambda functions. Postgres, we use a library called Serverless that kind of helps us manage Lambda functions. And we use a search database called Elasticsearch. So the meat of this talk is what we're calling 4 lessons about scale from Hotseat. So this is kind of, we're sort of assuming maybe you have like a web scraper or a small project, like how do you kind of go from that, like, you know, initial, maybe you're just running something on your computer to like, you know, you have a website that you want everyone at UCLA to be able to access. So these are like kind of 4 lessons we've learned in our process of scaling Hotseat up. A couple disclaimers before we start. It's okay, this talk is intentionally very high level. We aren't gonna make you experts in scalability. Tim and I have been doing this again for like the past few years. So, you know, we've had some time. So our goal is really to like throw pasta at the wall, kind of give you all the terms you need to know and think about so you can kind of start to know about these things at a high level, maybe like research them more on your own. And if you ever like need to solve these problems, you kind of know where to start and what to Google. Another disclaimer though, Tim and I are also by no means experts in this subject. I think like the more we dive into it, the more we're like, we don't know anything. So we don't have all the answers. This is kind of like where Hotseat is currently at this point of time, but it's like, you know, there are things we don't like about our architecture that we want to change in the future. So without further ado, 4 lessons about scale from Hotseat. So our 4 lessons, real briefly, database design, performance monitoring, and testing. So first up, database design. So if you're running something just like on your computer, you're doing like some web scraping locally or something, you can just like output like your results to like your terminal. You can like save them in like a file. Once you want to scale things up so you have them accessible to people, you probably want a database. Databases are very complex programs that make it very efficient for you to add and search data, and you can store things efficiently. And they're also much more reliable than files. Files are notoriously like fraught with like, you know, what if a computer crashes in the middle of writing a file? Do you get that data? Do you lose that data? There's this thing called ACID, which stands for like atomicity, consistency, something else. It's like a fun buzzword. You want that. You want to be able to handle multiple connections, right? Like what if 2 people are reading a file? What if 2 people try and write a file at the same time? Like who wins. And databases are also like much more well tested. They're written by like professionals who've been doing it for years. Postgres, I think, has been around for like over 10 years. So it's like much like it's battle tested, used by a lot of people. We know that there aren't going to be bugs with it. So there are two main types of databases. There's called relational, or often like SQL databases, or non-relational, and they're often called NoSQL databases, which is a bit of a non-term misnomer. Relational databases, as the name kind of implies, you're dealing with kind of, you call them tables, and you deal with like how they relate to each other. So in Hotseat, for example, we have courses, and a course is like an abstract version of a like class at UCLA. So it might be like Computer Science 31. And then we have sections, which are like concrete versions of courses. So like a section is like offer a version of a course offered for like a particular term with a particular professor at a particular time and location. So we say that a course has many sections because a course can be offered many times over many different terms. Non-relational databases are a bit more like loosey-goosey, anything goes, that you kind of just like, it's almost like, I'm not sure if you're familiar with JSON, but you just have data, you can kind of insert it whenever. You can still sort of relate things in a sense, but it's like they're just like rows in a table somewhere. There's not kind of like this relational type thing of relating different things together. Yeah. So the database schema is like an important term that we use, and it's basically just like, how is your data organized? So like, as I mentioned, like courses and sections, that's like a schema. We have like our courses and our sections. And you like, basically you can kind of create your schema by thinking about the nouns of your data. So for us, we have subjects and courses and sections, instructors and enrollments, and we kind of all sort of relate those between them. And you want to consider how the nouns relate to other nouns. And you also want to consider like, is it possible for like data to get invalid into your system? So like, like how do we, something we've dealt with a lot at Hotseat is like, how do we deal with instructors, right? Because like, can multiple instructors teach like the same section or not? Like what is valid, what is not? And you also want to consider like, is your data duplicated? Sometimes it's good to have your data duplicated in your database because it can make it more efficient for you to look that up. But obviously there's the cost of you have the same data in multiple places. It can go out of sync, and it's also double the storage space. So these are kind of the things you want to have in mind when you're thinking about your database schema. It's like a lot of not coding, but like thinking around and like diagramming and like, do these things fit together? For reference, this is like the Hotseat database schema diagram. So you can see we have subject areas over here in the top right, instructors, courses, terms, sections, reviews, users. These are like some analytics tables down here. So you can see it gets complicated really fast. And like, I know Tim and I kind of sat down and did a lot of diagramming to figure this out when we first started. And I'm glad we did, because it's helped us kind of grow in a sustainable way and not have to like, redo our database schema every 6 months. But speaking of redoing your database schema, how do you change your schema over time, right? Like obviously, like we've added features, we've changed things around, we've made things more efficient. Like how do we change our database over time? So the way you do that is via a thing called a migration. And that's basically a file that specifies how you change your database. Ruby on Rails, the framework we use, actually makes this super easy. So we can see you define a class and a method on that class called change. And then you can change the table or remove a column. And so it like provides us a very expressive way to change tables or change our schema over time. And you can see over time, like this is a folder of all our migrations since we first started Hotseat, and it's quite long. There are a lot of migrations we've made over time. So definitely like you want to track your changes to your database over time, because otherwise, like how do you get your data there? Like what happens if you lose your data? You want to make sure the schema is always there and ready for you. Awesome. So I'm going to hand it over to Tim now to talk about performance.
Hi, so my name is Tim. As as Eugene and like Nathan introduced, I am also a UCLA alum. Right now I'm studying computer science as a master's student at Stanford University. But yeah, so I'm super happy to be talking about performance. Performance to us is really important, and not just because UCLA has tons and tons of classes, but also because we want to do things as fast as possible to get people the most updated data. We also do things. We also want to do things fast, so we get to save on that computing costs because computers are not cheap or free. So yeah. So if you Nathan, yeah. So if you just try to do the naive thing of calculating how much time it takes to to scrape that HTML page on UCLA's scheduled classes, try to parse it and save the sections into a database. If you want to do all that for a single class, we calculated it takes usually around 200 milliseconds. But if you actually look at our current pipeline, to scrape all more than 3,000 courses offered for winter 2022, it actually only takes 1 minute and 10 seconds. You can try to mentally do the math, and you can multiply 3,000 whatever by like 200 milliseconds, and you end up with a number in the ballpark of like 10 minutes, 11 minutes. So how do we like do it so much faster? And the answer is really twofold. We employ something called parallelism and also something called concurrency. So parallelism is a paradigm where you run several things independently of each other at the same time, and this way you get to basically have things happen at the same time and therefore save time in total. Concurrency is a sort of similar concept, but it's a little more difficult to explain. It's less about using multiple like computing resources at the same time, and more about how to efficiently use a single computing resource, but have it do multiple things at the same time still. So usually we talk about concurrency for things like network requests. Sometimes you want to start like kick off a network request and like just wait for it in the background and deal with the response when it comes back. If you ever use JavaScript and you ever call like an asynchronous API or like the fetch API, you're basically dealing with concurrency at that point. So yeah, so in terms of how we use parallelism, so one easy way we do that is in basically dividing subject areas into separate instances of the scraper lambda function. So as you know, there are like more than 100 subject areas at UCLA, and scraping each of them can be pretty much done independently from everything else. And that's why we can just like feel free to start off a bunch of scraper functions and have them run in parallel, saving to the same database at the same time. For concurrency, that is more like we're employing concurrency within a scraper function. So inside the scraper function for, say, computer science, we can start off the request for CS31 while at the same time starting off the request for CS32, and we can sort of wait for them together. And that's like even within a single scraper function, we can do multiple things. And as you can tell, usually it takes like 100 milliseconds to contact UCLA registrar. And if we can sort of stagger the requests together, we will only need like less than 400 milliseconds to do two requests. So again, for our scraper functions, we're using the language Go. And Go actually is like famous for making it easy to do concurrency. So Go has this feature called Go routines, where basically you can spawn off these like mini threads, but they actually take up less resources than the actual operating system's thread. And we basically just spawn off one Go routine for each class they will want to scrape. And you can sort of see that at line 132, where we say go func, and inside that go func, we're basically scraping courses. And at the same time on line 130, you see that we have quite a few Go routines spawn at the same time, and all of them can run in parallel or run concurrently. Yeah. So all of this sounds pretty like expected, you know, the concurrency parallelism saves time, great, like that makes sense. But the real difficulty is in actually investigating how to correctly deploy concurrency and parallelism so that we avoid some common pitfalls. So the first thing is that web servers like those owned by UCLA, they generally have like a fixed upper limit on the amount of traffic that they can handle at the same time. If we try to like send 3,000 requests to UCLA server within the span of 1 second, it's more likely than not that their servers are just not going to be able to handle it and start not only rejecting our requests, but also requests of legitimate students trying to get information on the classes. So we need to take care of that. At the same time, for each of our scraper functions, they're running on a computer ultimately, and computers themselves have limits like hardware and as well as software limits on how many network connections can be made from that computer. Each of our scraper functions try to send data to the database, and the database software has its own limits on the number of network connections. Again, we're using Postgres, and Postgres actually is notorious for having a low limit in that regard. I think we can only do realistically do 50 parallel requests, parallel connections, even though we have, we spun off 100 scrapers for each subject area. And also finally, with concurrency and parallelism, because things are happening at the same time, it's really hard to reason about what's doing what, who's doing what, because things are no longer executing sequentially. So in terms of how we go about fixing these problems, it turns out that the first three problems can really have a similar solution, which is that we need to be more intelligent about when to start off a new parallel connection, and because of that, we sort of group them under the same umbrella of better scheduling as a solution to those problems. But more specifically, because we have both the scraper level parallelism as well as within a scraper we're doing concurrent things, we need to apply better scheduling to both situations. One thing you might have seen in one of the previous slides that we have a variable called num_routines, and through that variable we can control exactly how many requests are happening at the same time. Again, if you look at line 130, that num_routines is actually being computed from some environment variable that we're setting called max_routines. So because of that, we can control how much routine can be used. We start off with like a relatively small number, and as we gain confidence that the UCLA server can actually handle more connections, we like slowly increase that number to a good spot. At the same time, we also try to limit the concurrency and parallelism for spawning the scraper functions in the first place. So we mentioned, there are like more than 100 subject areas out there. At first, we really just like try to start all 100 scraper functions at the same time, and we slowly realized that it's not a sustainable approach, because even if we try to limit the parallelism within each scraper function, UCLA server is still not going to be able to handle that. Not only the UCLA server, but also our database software. So we try to limit the concurrency there as well. And finally, the effective reasoning constraint. So that is more for like debugging purposes. When we are trying to debug some code, we really want to know what happened before what. And because of that, the solution we found to be the most useful to us is monitoring, which is the topic we're going to be discussing next. So yeah, monitoring. The general premise of monitoring is how do we know when things go wrong? And so one example is that we have a Slack server, and whenever something will go wrong, we have this service called Datadog that's going to alert us, hey, the number of errors in this fetch sections function is a bit higher than it usually is. We're going to be talking specifically about 4 different methods of monitoring: logging, tracing, metrics, and alerts. So we actually just saw alerts, right, from Datadog. Usually it's something that gets sent. It's a message that gets sent to Slack. Sometimes companies in the industry would use solutions like PagerDuty, and these are things that usually get triggered by certain events that people set up. Like if we have a lot of errors coming from a service, that would trigger that alert. Usually there's like some sort of quantifiable thing that you have to manually set up. For logging, I'm sure many of you are familiar with the idea of logging, but just from like doing computer science projects. But yeah, the general idea is it's just a fancy print statement. But there are some nuances that we want to talk about on that topic. So tracing is a way for us to track how much time our applications take, and not only how much time our application takes in general, but also like how much time each part of it takes individually. And that can really help us track down performance problems. We also have metrics, which is just like quantities that help us understand how our service is performing. Is our website up? How often is it up? Is it up 100%? Is it up like 50%? In which case it will not be very good. How is our database performing? How many records are we processing every second? How much time is our scripter taking? All of those would get categorized under metrics. So yeah, let's look at some examples. So we use a service called Datadog, which has a lot of like fancy features for doing metrics and tracing. And here is a dashboard that we set up for metrics. As you can tell, we have on the left-hand side, we have like the average lambda durations for each of the functions we have. On the right-hand side, we have like within the past 2 hours or within the past whatever hours, how much time is spent doing a particular action through lambda function. We also have like some estimate costs on the bottom right panel. For logging, so logging again is just like really just printing a message. But at the same time, we find that sometimes adding more information to the log can be really useful for debugging. So if you look at one of the lines on the right that starts with like MSG, you'll see that not only do we include the message, but also usually some other metadata corresponding to that particular log line. For like no website found or could not find final time, we have a key called course, and that course contains information about which course are we talking about when we're trying to say we could not find final time. And one good thing about Datadog, and this is also a feature in many other systems like this, is that you can actually search for a particular key in the logs. So if you know that like if you go to our website and you see the course that is not just like the course page is just blank or it's erroring out, then you can tell us the course number and we can literally just go into the log, ask Datadog, hey, please filter by this subject area and this course number, and Datadog can tell us the logs that led up to the potential failure. So this is like how we're doing logging in action in our code. So in Go, we're using this library called logrus, where not only can we define like the severity of the logs, is an error, is an info, but we can also include like structured information like terms or the actual error. And these things basically go to the dashboard you saw on the previous slide, where we can see the individual properties within each field. And we have a similar approach for Ruby. Ruby on Rails comes with a built-in logging library, so we're just using that. And you can tell on line 59, we have logger.error, which is basically saying, hey, there's something really bad happening. And finally, so like if you're just working on like CS projects, a lot of times you don't really think about like something we call log levels. But if you're having like a full-fledged application, you really want a way of organizing the logging you do so that the general severity, how important a log generally is. And like many different libraries have different terminologies, but usually they all have like something like info, which is like a normal routine actions. We want to know like what's happening, but at the same time, it doesn't indicate anything bad. We also have warn or warning, which is worth looking at if we're debugging an issue, but probably not so bad in itself. And error, which is something's definitely wrong. We definitely want to take, like if this happens, we would definitely want to take a look. And usually, if you're setting up alerts, this is the last level is probably something you want to select and alert on. Like if you have like 15 error log lines within the past few seconds, then something is probably really, really bad. Yeah, so we also found adding log lines when you fix the bug to be very, very useful. Like if you're working on a bug and you add a log line, not only do you get to like have deploy this fix software into production and try to like verify through the log that the bug was actually fixed. So you could do that. But also it's important to notice that like researching software engineering has shown that if you fix a bug, then it's usually more likely that there are more bugs in the same vicinity of the code. And adding log lines near where you fix a bug can actually save you time in the future when you inevitably have to debug the same code again. And finally, as I already mentioned, adding helpful metadata to your logs makes it really easy to just search for all the logs corresponding to a particular set of criteria. And that, context really helps. Yeah, so the last thing I want to talk about is tracing or traces. So once again, we're using this. Tracing is how you can debug the like additional performance issue in your code. So within this particular graph, we can see that the whole fetch sections lambda function took like less than 1 second, but within this we can see HTTP request takes like around 133 milliseconds. Another request takes less than 100, and there are some other things next to it as well. So let me give you an example of how this can be really useful. So before we started doing tracing, we saw that our scripters were running pretty slowly, but like at that point we're just guessing like what's slow. So we thought it could be that like UCLA's website is slow because we knew we were hammering their servers pretty hard, but after we added the tracing, we saw that it wasn't actually the HTTP thing that was taking a long time. It was actually doing the database queries, the database insertions. So we did a lot of optimization in that area. We tried to like batch queries together rather than sending them off one by one. We also tried to move our server, move our lambda and all other things into like the same AWS region so that network latency will be lower. And now if you look at it, the green part is actually very small compared to the purple HTTP request parts. And that's that's an indication that we were able to mostly address the database issues we're having. There's also, you see that we have many pink lines that overlap with each other, and that's just another indication that we're doing things concurrently at the same time with each other. So that's good too. Yeah, and how exactly we're doing tracing is we made our own library that basically gives you both the logger as well as a new span. So each line you saw in the tracing graph is technically called a span, and you can basically set some attributes to the span, like subject areas and other things. So yeah, Nathan, do you want to take over for testing?
Yeah, I'll take over for testing. So final lesson is testing. How do we test at Hotseat? Most of our tests at Hotseat are actually in our Ruby on Rails code, because that's the part that users interact with the most. So we want to make sure they have a good experience. So this is like a traditional Ruby style test using a library called rspec. And the notable things about it are you kind of like describe, like you kind of write your tests like human code, right? Like a test is computer code to test your computer code. But our spec lets you kind of write it in a more human way. So we're describing a user, and a user should always have a name. So then we test a user is valid if they do have a name, and a user is invalid if they don't have a name. Pretty straightforward. So we also have a front end at Hotseat. Like I mentioned, it's kind of written in, there's a lot of JavaScript and React. We don't really test a lot of this code. Part of it is because we change the UI pretty frequently. So it's sort of like we're testing something that's moving very fast. Another part of it is like at its core, Hotseat is we're displaying data that we have from the back end. So really, like if we write, like we essentially have to, like, if we aren't testing the back end, we need to like kind of mock this data up in the front end. So we're testing it, but then it's like, if the data changes, we have to change the test. And then it's like, if the data changes, then maybe the test still passed. So it doesn't really tell us anything. So we kind of found it's just like simpler to not really have JavaScript tests for the most part. That being said, we do have a fair amount of what we call end-to-end tests. So this is what tests the whole system. So we test the JavaScript, we test the Ruby, we test the database. And we basically do this through a program called Selenium, which is basically like a way for you to write scripts for a web browser. So you can see kind of at the top of this test, it says driven by Selenium Chrome headless. So we're basically running an instance of Chrome with this test. In this test in particular, we're testing that a user can write a review for a course. This is like a pretty core important feature of Hotseat, so we want to make sure that it doesn't break ever. And so this is why we're testing it in an end-to-end manner. And you can kind of see, like at the top, we're setting up the database, and then we're like navigating to a URL, and then we're like clicking buttons on the browser. So the con of end-to-end tests is they're slow because we can't, like, you know, we have to run a web browser and things like that. But the pro of it is it allows us to give us a high degree of confidence that these features work like totally, completely in production. So that's how we test our Ruby on Rails application. But how do we actually test our web scraping? So when we're getting data from the registrar, when we're saving it to the database, how do we test those? So if we think about it, going back to our diagram, there are kind of like three different parts to web scraping, right? There's the registrar, the website we're scraping from. There's the actual code, the scraping and the parsing. And then there's where we store that code in our database. So thinking about these three parts, like each at the beginning, it doesn't really make sense to test the database. Like I mentioned earlier, the database is very well tested already, written by people much smarter than me and Tim. We can kind of assume that the database will work, it won't lose our data. Likewise, it doesn't really make sense to test the registrar website or like the network, because we know the people who wrote Go, they're very smart. They wrote very well tested and reliable networking features. And the registrar website, we have no control over, right? If the website goes down, that's like, we're out of luck. We can't scrape that. The thing that we can control that is likely to have bugs is our actual parsing function. So how we transform the HTML into a format readable that we can store in a database. This is actually just an example of last week, a parsing issue we ran into where the registrar website, basically they decided to change links into buttons, and that just broke our scraping. We had to rechange it. It was a one line or a one word fix. As you can see, we just changed the link to a button, but we were like, why aren't there results coming in? And that's the reason why. So example of why it's important to test the parsing. But on the other hand, also like because the website can change, we also don't want to write specific tests for these like HTML files, because, you know, the registrar could just be like, links are becoming buttons, and then all of our tests, like we'd have to rewrite those. So the way we get around that is via a type of testing called golden testing. This is pretty popular in the Go community. And the idea of golden testing is you have fixtures and you have golden files. you can kind of see from this code, we're reading a fixture, we're doing our parsing, and then we're checking that we match this golden file. So basically, the idea of the fixture is it's a file that has some data. It's sort of outside of our control. In our case, it's HTML files from the registrar. The golden file is kind of an output, like it's a snapshot essentially of the results from our parser. So let's look at an example. So this is the golden file, just a lot of HTML from the registrar. Or this is the fixture file, sorry, excuse my confusion. This is the golden file. So this is basically a snapshot of what the parser outputs after it does all its parsing. So you can see it's just in JSON. We have like number and title and this model thing. And the advantage of this is we can diff this against previous versions of the golden file because we store this all in a version control system. And we can see if there are any changes in the HTML file, how that changes the golden file, and we can update those easily without actually having to update the actual test that we wrote. So this is an example of running the test. It's a little bit contrived, but you can see I changed a header to say operating system principles, blah, blah, blah. And our test failed and it told us how it failed. It said, we expected this title of operating system principle, but it was actually blah, blah, blah. So this is super powerful. And then we can just run a command go test update and that automatically fixes it. So it's like awesome for if the registrar changes something on us, we can just re-download their files, rerun our tests. If anything's broken, we can kind of see where they're broken easily, make those fixes, and then ensure that the golden files are always up to date. So kind of in summation, our Hotseat testing philosophy, test your core server code a lot, because that's actually the user oriented part. Don't really worry about the front end testing, end-to-end test the important things, and use golden test for web scraping. I think that's worked really well for us, and I'm really happy with like our testing situation for the web scrapers. And a bonus, we also really recommend having automated testing set up on GitHub. So we just use GitHub Actions. You can kind of see it's super simple to set up on the right. Like we can see we just install Go, we check out our code, we run this go test command, and then we upload the code coverage. And on the right, it gives us like awesome like check marks and X's of when things are successful and breaks. And it gives us like a lot higher degree of confidence of like, oh, this change is safe to merge, or this change will introduce a bug. We've caught numerous bugs from this, so it's been super high leverage. And yeah, you made it. That is our 4 lessons of scaling Hotseat. Thanks for coming. I'm going to hand it over to Tim to kind of close us out.
Yeah, can go next slide. Yeah, so so a lot of things we talked about today, we actually already wrote about it. And as Nathan described earlier, this whole project really came about from his independent study project, and he has 2 really well written blog posts on that topic on his website. So if you're more interested in like how we did the parsing, like how we went from HTML to database, those 2 posts can really help you, even get started on your own scripting project. We also want to, like discuss some CS classes at UCLA that where these things we talked about today are taught. So CS 130 software engineering, it covers like a lot of different material, but one of them that really stood out to us is like the focus on testing. And they teach like some testing like methodologies and philosophies that we found to be really useful to us. If you're interested in more like how different programming languages deal with concurrency and parallelism, CS 131 is your friend. And for our project, we use a lot of SQL. We use like a SQL database. And SQL is actually a pretty complicated language. And if you're interested in learning more about it, CS 143 is really useful. So I personally did not take this class, and I am regretting it. So that's why for my master's degree, I'm definitely planning to take something similar. And finally, there's also the scalable internet services class. That's a CS 188. And in that class, you learn more about like AWS cloud computing, as well as some networking basics. And finally, we have a blog at blog.hotseat.io. We have some posts on new announcements of features, and we're also planning to write more about like engineering and how we do tech on that blog. So keep posted if you're interested. And yeah, so that's it. That's all we want to talk about today. If you have any questions, please reach out to us at the email address listed here. And yeah, also just let us know if you have any questions right here.
Yeah, we can take questions live or on the chat too.
Yeah, so we have a question. What is it that the UCLA server can't handle? Is it because there are so many web browsers opening UCLA registrar pages at the same time to do the scraping? Yeah, that's exactly the idea. When we send like 3,000 requests to the UCLA server at the same time, either they will decide that they can't handle that many and just give up, or they can decide, hey, like, we can probably handle this, but it's going to be a slow process because we have to work through all the requests that's coming in. So yeah, so when we do scraping, we don't actually use web browsers to do the scraping, but instead we just like send the HTTP requests from Go directly. But yeah, the idea is very similar. It's also very similar to like if you have many students trying to enroll in the class at the same time. Same idea. Yep, HTTP requests.
I have a question regarding, I guess, deployment. So I know there's like a lot of different components to like, I guess, a whole like architecture as a whole. So like, for example, if UCLA changes their, as you mentioned before, changes something about about their HTML files, and you need to make a change. How does like deploying that change? How do you guys like manage like deploying that change and making sure it's like working across all the other components? And have you run into any issues related to that?
Nathan, do you want to handle that?
Yeah, that's a great question. That's kind of, I think deployment's actually kind of like one of our honorable mention topics that didn't make the cut for this talk. So like you mentioned, yeah, we have like a bunch of different components. So we deploy those components in different ways. So the Ruby on Rails application itself, it's just a Heroku application. And it's super simple. We can like, get pushed to main, and it'll like auto deploy a new version of that. And the Lambda functions are more complicated. So the way AWS wants you to deploy Lambda functions for Go is you basically have to compile the Go function locally and then upload it to S3, and then like Lambda will like pull it from S3. It sounds complicated. It's actually not as complicated as it sounds because we use this tool called serverless, which is, I think it's like a framework or kind of tool. It basically handles like kind of making API requests to AWS. So we can like give it a like Go function binary, and it can kind of just upload that to S3 and sort of like create the corresponding Lambda resource for AWS. We have like a make file that sort of wraps serverless. So we can say like compile all the functions and then deploy them super easily by just like typing make deploy. I think like that's something we definitely would like, I would love to automate that in the future. So like if we just push to master, like the Lambda functions just like auto built and deployed. But currently like that process is a little more manual. And then for like the database and search and stuff, that's all managed through AWS. So we don't have to really like worry about deploys in that sense. It's kind of just like they handle it, which is very nice.
Yeah, I also want to add two more things. So for the AWS things, like the database servers that we have, so we're using something called Terraform, which is like a pretty popular tool for managing for managing like cloud infrastructure, you can basically write your configurations as code and commit it into the same repository. And whoever wants to deploy it can just run the command that's going into AWS to update all the configurations, all the knobs and switches and such. And also another thing with Go is that Go actually compiles down to machine code, much like C and C++. So that actually can make it a bit tricky if you're developing on a MacBook, but AWS Lambda, they run on Linux. So you want to make sure that you can cross compile the project for a different architecture. Unfortunately, Go makes it pretty easy to do that. You can just turn on a switch through an environment variable, and it's just going to output a different binary. And that's pretty different from C and C++, where usually cross compiling is a lot more difficult. Yeah, so I see we have quite a few more questions. So are you planning to integrate some of the UCLA API developer portal features to Hotseat? So I think that's actually a pretty like new development. When we started doing Hotseat, I don't think that really existed. I personally think things are working pretty well for us, but we also know that there's some changes coming on the horizon, like moving to Canvas from CCLE. So we're definitely keeping an eye on that, but at the same time, if it ain't broke, don't fix it, right? So like, I think for now we can just stay where we are.
Yeah, I think last time I looked at like the API, it like required authentication and like you had to be a staff or something. So maybe that's changed since then and probably worth like relooking for us. But if it ain't broke, don't fix it.
Yeah. In your design process, did you guys make pros and cons for the different frameworks and stack you will use to achieve what you guys wanted, or did you guys already have a strong idea of what you wanted to use? Yeah, that's also a super interesting question. I think it depends on which piece we're talking about. So Nathan is very well acquainted with Ruby on Rails, while I'm personally more familiar with like Node.js. So like I think because he started the front end servers, I think we just went with Ruby on Rails. But and that's not fine. I got to learn Ruby. It's great. For the scraping though, like for the lambdas, I think at first we sort of had some proposals of just like using one of our spare computers as a server to just like run the scraper once every hour or something. And then we discussed it and realized it's not as easy to maintain as something like AWS Lambda. So yeah, I think we like definitely had conversations on quite a few different areas, but at the same time, like it's a lot of it really came down to what we know and what we have previously worked with. Like we both worked with Go. I used to be at a company where like Go testing is quite a big thing. So yeah, that definitely informed our experiences.
Yeah, I'd say something I'd add to that is I think I talk about this in one of the blog posts we linked to, but I originally wrote like I think Python's often like used as like the like a great web scraping language example because it has a lot of great libraries and support for parsing HTML and stuff. And I originally wrote like the first scraper version in Python. And it was kind of once we ran into these concurrency problems that Tim talked about, did we realize like, oh, Go kind of makes a lot more sense for what we're doing. It's a lot more like verbose of a language than Python, but it kind of gave us these, like it gave us Go routines, whereas like a big selling point. And we eventually like rewrote all our functions in that. Ruby on Rails, something that was really appealing to me when I was first picking out the technology was the migration feature we talked about, like just being able to manage your database schema over time super easily. I think like it's much tougher to do that in something like Node, where you're writing a lot of these things like for yourself. Ruby kind of, it's like very batteries included, like it gives you a lot of nicety feature things. As a result, it's kind of like opinionated about how you do things, but it's very nice for just like getting something built fast. So yeah, a lot of it was just kind of like what we're familiar with or what we'd heard about and we're interested in using. But there were like some kind of motivations behind specific technical choices. I can take I think the next question is, do you have a public API that others could use to get some of the course data? That is something that we currently do not support, but is something we would like to do. I think it's kind of just, we've been working on like notifications and adding like features for users. So that's just something we haven't gotten around to as much. But if you have a cool idea for like something you could build on top of the Hotseat data, email us, let us know. We'd be super like happy to chat with you about that. Are you guys sending HTTP requests to the UCLA registrar servers? Yes, we are. So we just, Go has like an HTTP request library you can do where you basically give it a URL and it kind of gives you back the response from that URL. And that's exactly what we do. It's not really like an API because it's not like the pages we're scraping aren't really like intended for consumption by like robot scrapers like us. So I think that's kind of like the difference between like web scraping and APIs is like APIs are sort of meant for people to use them, and scraping is sort of like the data is there when we're just going to like pry it out of your website, whether you like it or not.
Yeah, to expand on that, we are basically doing, we're basically requesting the same page as what you would see when you actually go to the scheduled classes in a web browser. So yeah, we're definitely not using like, there is no nice API for us to use, unfortunately. So.
Is this a side project for us, or do we plan to make it something more? I think like it's definitely like a little, like it's definitely a little more of a professional side project. I think like we've been working on it for a while. It's not just something like a little like, you know, work on it for a couple months and like toss it away. But it is like, I think Tim's not planning to like drop out and like work on Hotseat full time, and I'm not planning to like quit my job to work on Hotseat. I think it's like, we acknowledge like it's probably not going to like pay all the bills and everything, but we have fun with it. So it's like a more professional side project, I guess, is how I'd phrase it. Expanding to other schools. We're asked if we want to expand to other schools. I think maybe one day, yes. But currently we're kind of just focused on like making Hotseat the best it can be for UCLA. And we'd kind of want to, you know, feel like Hotseat sort of feature complete, or like can kind of stand on its own, and a lot of people are using it and everything like that, before we try and like bring it to other schools. And yes, so I started this in summer 2019 was like the first original version of the scraper. And then I guess like Hotseat in its kind of like current modern website forms we've been working on since like summer 2020. Awesome. Well, if there aren't any more questions, thanks for coming, everyone. We really appreciate it. Check out Hotseat again, shameless plug. It's like totally free. Lots of super awesome features. And yeah, hopefully you have all good enrollment passes this upcoming winter.